Good morning, Doctor. We are from Group 6, and today we are going to present our project entitled Astra AT-2 Conceptual Aerodynamic Design of a Two-Seat Sport Aircraft Wing using Fundamental Aerodynamic Theory. In this project, we apply the aerodynamic theories learned throughout this course to develop a conceptual wing design for a two-seat sport aircraft. My name is CHEONG with matrix number 231520, and I will begin by introducing our project before my teammates continue with the technical analysis. Next. I will first introduce the project, followed by the engineering problem, design requirement. My teammates will then explain the aerodynamic theories, wing design, engineering calculations, and final evaluation before we conclude the presentation. Next. So for every successful aircraft, we begin with a clear mission. So for Astra AT-2 is a conceptual two-seat sport aircraft designed for recreational flying and flight training. Since it is intended for training, the wing must provide sufficient lift, stable handling, and good aerodynamic efficiency. We selected the Diamond DA20 as our reference aircraft because it has proven aerodynamic performance. Using it as a reference, we developed the conceptual wing design of Astra AT-2 by applying aerodynamic theory and engineering analysis. Our objective was to achieve a balanced design with a good lift, low drag, stable handling, and improved fuel efficiency. Next. Every engineering project starts with a problem statement to be solved. For our project, the main question is how can aerodynamic theory be applied to design a two-seat sport aircraft that provides sufficient lift, low drag, stable handling, and good fuel efficiency. This requirement must be balanced because improving one performance may affect another. Therefore, our goal was to develop a wing that satisfies all design requirements rather than just focus on only one characteristic. Next. Based on the engineering problem, we established the main design requirements for Astra AT-2. The aircraft is designed for recreational flying and flight training using the NECA 2412 airfoil, a moderately tapped wing and an aspect ratio of approximately 10, a wingspan of about 10 to 11 meters, and a wing areas of approximately 11 to 12 square meters. On the right is the engineering workflow that guided us for our entire project. We started by defining the engineering problem and mission requirements, followed by studying the reference aircraft, selecting the airfoil and wing geometry, as well as performing engineering calculation and aerodynamic analysis, finally evaluating the complete wing design. Then I will now hand to my teammates to further explain the lift generation analysis and thin airfoil theory in a more detailed way.
My name is NURALYA BALQIS. I'll be explaining the lift generation and also thin airfoil theory. For the aircraft data, we actually got the data from the website for aircraft DA20, and then we find the required lift force for the aircraft and then the coefficient of lift to further use by thin airfoil theory to evaluate if the airfoil can efficiently produce the exact amount of lift. Next. So the airfoil that we choose is NACA 2412, which will give us the data of maximum camber 0.02, position of maximum camber 0.4 from leading edge, and maximum thickness 12% of the chord. So the equation that we obtain is from the standard NACA equation, which then will be differentiated to obtain local surface slopes, which is the dz over dx for the front and side airfoil. And then the slope will undergo Fourier space and transformation, which will transform the position into angular coordinates to evaluate thin airfoil integrals. And then the integrals will be used to determine the essential Fourier coefficients, which we have A0, A1, and A2. From the A1, we will obtain the alpha node, which we then substitute into the coefficient of lift to find the angle of attack required for the airfoil. Then lastly, the aerodynamic traits can be determined using the data that we obtain. That's all from me.
So my name is SYAFIRA with matrix number 280. So now we will talk about the drag and wing efficiency. So for our drag and wing efficiency profile for our two passenger sport aircraft design, so geometry has a wingspan of 10.7 meters and a wing area of 11.1 square meters using a high aspect of 10.2. So to account aerial lift distribution losses and wing vortices, we calculated also efficiency factor using Raymond's empirical formula for straight wings. So substitute aspect ratio into the equation gives an efficiency factor of 0.751. So this signifies an excellent span-wise efficiency of 35.1%, demonstrating that our wing geometry effectively minimizes aerodynamic uses additive. So next we model our total cruise drag coefficient using the classical drag polar equation combining parasitic drag and induced drag. So first we have to evaluate the aircraft at its maximum lift to drag of 14, where parasite and induced drag are equal. So we isolate a baseline parasite drag coefficient of 0.0207. So secondly, we have to further study level cruise at 67 meters per second, balancing our 7848 Newton gross weight requires a lift coefficient of 0.247. So applying this to our induced drag equation yields the 0.025. So this brings our total cruise drag coefficient to 0.0332. By inputting this into fundamental fluid drag equation, we determine that the aircraft requires a total thrust of vector of 1059.5 newtons to overcome fluid resistance at cruise speed. Thank you.
So next, my name is Amalia and I'll present about the airfoil selection comparison. So we evaluated 3 candidate airfoils. The symmetric NACA 0012 was rejected because its lack of camber requires high cruise angles of attack, which creates excessive drag. Conversely, the heavily cambered NACA 4412 offers high lift but causes an unstable nose-down pitching moment. Therefore, we selected the NACA 2412 as it delivers the optimal balance, which is an ideal maximum lift coefficient range of 1.4 to 1.5, low drag, and highly predictable handling stability. Next. Next is for the final airfoil selection and justification. Looking closer at our selected NACA 2412 profile, its geometry features a 2% maximum camber and a 12% maximum thickness. This design directly validates thin airfoil theory, creating efficient lift at cruise, which is physically governed by the Guta condition at the sharp trailing edge. For student pilot safety, our airfoil tools polar data confirms a gentle trailing edge stall mechanism. Because flow separation travels slowly from back to front, the outer wingtips and ailerons remain in clean flow, granting the pilot maximum roll control when they need it most. Lastly, the 12% thickness provides the ideal internal envelope to house a robust wing spar without adding any profile drag penalties. Thank you.
So my name is Muhammad bin JIHAD, reference number is 228751. So for the Astra AT-2 fin geometry, we uses the A20 as a reference. So it has a high wing composite construction with integral winglets that can induce drag and improve roll stability. The wing also has washout, so the root stalls before the tip, keeping the ailerons effective near stall. Next. So the wingspan is 10.87 meters, wing area is 11.61 square meters, max takeoff weight is 800 kilograms, empty weight is 528, so payload capacity is 272 kilograms, enough for 2 passengers and baggages. Next. For the aspect ratio formula is span squared over wing area. That gives us 10.87 squared divided by 11.61, so that gives us about 10.2. That's fairly high for a light sport aircraft thanks to its glider heritage, and it gives a good glide ratio of 11:1, though it does add structural weight. Next. For the wing loading is weight over wing area. That works out to about 676 newtons per square meter. High wing loading like this means gentler stalls, shorter runways, and good training characteristics. Next. For the lift equals half times air density times velocity squared times wing area times lift coefficient. In level flight, lift equals weight 7,848 newtons. So at cruise speed of about 67 meters per second, solving for lift coefficient gives us about 0.25, showing the aircraft cruises well below stall. Next. For the stall speed calculation, we use a square root of 2 times weight over air density times wing area times max lift coefficient. So from the website, we got the diamond list. It at 45 knots with full flaps. So working backwards gives us a max lift coefficient of about 2.06, combined with the high wing loading that gives the Astra AT-2 a safe, low stall speed ideal for training. Thank you.
Hi, my name is NURALYA FAUZAH, binti Muhammad FAUZI. So I'll be explaining about the final wing design. So the design actually we adapt from the DA20. So it actually achieves good aerodynamic performance while remaining structurally viable. So the high wing provide better inherent lateral stability and better ground clearance. So the aspect ratio actually minimizes the induced drag during cruise, maximizing fuel efficiency and also training flight endurance. So the aerodynamic theory integration is that the thin airfoil theory dictates a lift slope of 0.11 per degree. So the 2% chamber shift, the linear lift slope from -2 degree up to 12 degree. So actually provides steady lift at cruising altitudes. So the sharp flow at the trailing edge actually satisfies the Kuta condition. So for the 3D flow, which is the induced drag minimization, so the high aspect ratio actually forces an approximately elliptical lift distribution and also minimizing the induced drag. Next. So for the hand sketch and also the design specifications, as you can see, the leading edge is actually 0 degree, which is perfectly straight. So also the highest point of the curve is actually camber at 40% chord. That's all. Thank you.
Okay, so my name is Muhammad IRFAN bin ROSLI. My matrix number is 229948. So I'm going to continue this slide, which is the advantage, which is the Astra AT-2 used the NACA 2412 airfoil to achieve an excellent balance between lift and drag. Its chamber design generate positive lift even at low angle of attack, improving takeoff and low speed performance. The 2% chamber and 12% thickness provide stable flight characteristic with gradual stall behavior for safer handling. Combined with a high aspect ratio wing of about 10.2, the design reduce induced drag, achieve around 75% span-wise efficiency, and improve cruise performance, fuel efficiency, and overall aircraft endurance. So for the next one is the limitation and future improvement. So first I can say is the design has several limitations. First, it relies on thin airfoil theory, which assume ideal two-dimensional airflow and does not account for turbulence, viscosity, or flow separation. Second, the aerodynamic performance is based on the theoretical calculation without detailed CFD validation. Finally, while the wing is aerodynamically optimized, further structure analysis is needed to evaluate bending stress, material strength, and long-term fatigue performance. For the future improvement, I can say is the can further enhance the Astra AT-2 wing design. First, CFD simulation should be used to analyze the real airflow and improve the accuracy of lift and drag prediction. Second, the finite element analysis can optimize the wing structure, including the spar design, material section, and weight reduction. Finally, advanced such as a winglet, wing twist, and high lift device like flap can further improve aerodynamic performance and efficiency. Next, the other person.
In conclusion, our team successfully developed the conceptual wing design for Astra AT-2, a two-seat sport recreational and flight training sport aircraft. Every major design decision was supported by lift equation, thin airfoil theory, the Kuta condition, angle of attack, and induced drag concepts. Overall, this project demonstrates that fundamental aerodynamics theory can be successfully applied to develop a safe, stable, and efficient conceptual wing design.
So this is the reference that we use for this assignment, as you can see, doctor. And then lastly is thank you from us.